start? Oh, really full. Right, thanks for coming. So this week we have Professor Mihyun Kang from TU Graz in Austria. She will talk about phase transition, random graphs, hypercubes.
First of all, thank you very much for the kind invitation. And second, it is my great pleasure to meet so many fellow mathematicians in my home country. I visit Korea from time to time, but as a private person. But this time I came here as a mathematician. And I realized that Sang-il and Hong are hosting one of the largest combinatorics group in the world. Indeed, it used to be somewhere else, but apparently there is a huge community. I'm very happy to see that development, because when Sang-il and I studied some discrete math, it was not the case anyway. So let's go to the main thing. So I will talk about phase transitions, random subgraph, and hypercube. Maybe there are three keywords that some of you might not know. So phase transition, what they could be, random subgraph, and hypercube. I will explain that. First of all, phase transition is the thing that you might experience everyday life, in particular in summer. You see that according to the temperature, the water becomes vapor or gas around some number, some Celsius, and also some ice. It's not now, but in winter, you also see a phase transition from ice to water or water to ice around 0 degrees Celsius. Such a sudden change in some system by altering a particular parameter, we call phase transition. Some phases are in transition from one to the other. So there will be some properties changing according to some parameter. Here some parameter will be indeed by definition of a random subgraph. So it depends on how you select the random thing, but I will explain that. And then there will be base graph, which is so-called hypercube. So let me just tell you what my plan is. So in this particular topic, I will be focusing on the so-called giant component. We look at the connected component, and depending on this random parameter, certain things will appear, certain things will not appear, but in this particular case, we will be interested in the largest component. Among the components, the largest one. Then, as a kind of a method, what we could prove, we will derive as a consequences of the so-called isoperimetric inequalities, or sometimes we call expansion properties. It's not necessarily the expansion property that you might use in the structural graph theory or the width parameters, but the classical expansion properties. Then I will talk about some almost spanning structures, in particular matchings, or long cycles. That will be the main topic. At any point of the talk, you can just stop me and ask questions if things are not clear. Let me set the scene first. In reverse direction, hypercube. What is a hypercube? Given D, which is an integer, natural number, we will be talking about D-dimensional hypercube. We will consider it as a graph, not as a Boolean lattice, but we will consider as a graph with a vertex set. What is a vertex set? It's just binary string of length d. Each coordinate has either 0 or 1. For example, if d equals 4, I illustrate this, but it's a so-called Hesse diagram, but don't think about it. So just a combinatorial object, the graph. Vertex set, just binary string of length d. And edge set. What is an edge? There is an edge between two binary strings, if and only if they differ in exactly one coordinate. If you start from 0, 0, 0, 0, when d equals 4, it is neighbor to one of these if you flip one of each coordinate. So it has 4 neighbors, and also it's neighbor if you flip one of the 4 d coordinates. Blah blah. So therefore, you can think of this as a graph with a very nice structure. Namely, trivially, we have d2 to the d many vertices. Every vertex has d neighbors because we can flip each coordinate, and it is bipartite because the edges exist if and only if they differ exactly in one coordinate. If things are different by 2, then you see that there is no blah blah. And what is nice thing about small diameter? Namely, you can reach from bottom to the top by flipping just each coordinate once. So you can reach from any vertex to the other by flipping the coordinates. Yeah? So diameter is d. Other properties are also known. So dot 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 is it also has to do with the gray code, blah blah. But my focus is not that. There was a second keyword about random subgraph. What is that? It's a very general concept. Given any graph, base graph, you can make it sparse. How can you make it sparse? Is either via deleting some of the vertices and instead edges, the so-called vertex population, but we will not do that. We will do the so-called edge population. What we were going to do is, given that base graph, throughout the whole talk, my base graph is the hypercube, yeah? D-dimensional hypercube. And D you have to think about as a D large. It's not a 2, 3, 4, but really large number, but fixed. Now, given probability P between 0 and 1, what you do, for each edge in the base graph, we flip a coin with probability P, we keep the edge, and with the probability 1 minus P, we do not delete that edge. So this red thing, each such an edge, we fill up a independent coin, and we keep it with the probability P. Yep. As a result, we are making this graph sparse because we are selecting only fraction of the edges given by probability P. As a result, potentially, diameter might become larger because we make it sparse, potentially larger, and so on. Yeah? So the very first question in this model, it indeed is not a very new model, it's a very old model, already from Ederschuh and Spencer. They ask, when does the so-called giant component appears for the first time? What is a giant component? Is a component. What is a component? The partition class of vertices, so that every pair of vertices there is a path. What is the component whose order is much larger than the order of the second largest component? And it's a kind of giant in the sense that the order is much larger than the other. And if it's a unique, sometimes there could be many such giants, but usually you also talk about the unique giant. So when does the giant appears for the first time? Of course, we are talking about probability experiments, so we can talk about typically, so with high probability. Probability tending to 1 as D tends to 2 and D.
Well, I wanted to make two regular.
Two regular?
At least degree.
Why do I need degree 2?
Otherwise, it might be like matching, right? If it's too low, then.
Very good approach.
Yeah.
Yes, but I can make it smaller. Very good guess. But this can be smaller. 2 is a little bit, I'm paying too much. Let's do the thought experiment by PFS. I start from one vertex, let's say 0, 0, 0. If I have an edge or child, then I can continue, right? For each this one, if I see at least 1, I think that's why you have a degree 2, huh? In your brain. At least 1, maybe from time to time I have 2. It's a so-called branch BFS. We are exploring the component containing a particular vertex via the depth breadth first search. Breadth first search, I don't go depth, but first I explore all these potential neighbors. We have a potentially D of them, right? Potentially, but with probability P. So in this case, something. Yeah? I will explore. This is the average degree. Yeah? This is the average degree. I don't know what average degree C. So P times D is the number of vertices that I will see from my point of view. Yeah? And then I will do the breadth first search as well. Blah 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 blah. Then this breadth first search type of component exploration can be coupled with the so-called branching process. Have you heard about branching process? You start from a vertex and then we couple, right? Branching process for each vertex, you have a same degree distribution. Let's say Poisson, yeah, because on average we will see P times D many children. So let's say Poisson branching process with Poisson C, independently Poisson C many, maybe sometimes more than 2. From the branching process theory, if number of children, expected number of children of a given vertex is larger than 1, it continues forever with a positive probability. If C, expected number of children, is smaller than 1, then it dies out. Yeah, this is very well-known theory by branching process. So there is a so-called subcritical point and supercritical point. Yeah, it dies out forever. In this case, with a positive probability, it continues forever. On the other hand, branching process is an infinite process, while our graph process is finite, and also potentially we have C4s or small cycles. Yeah, it's not exactly the same thing. That's why I call coupling. There is such a coupling, whatever it means. Therefore, our intuition says, indeed, as Sang said, the criticality is not indeed a 2, but almost 1. Yeah? So indeed, it was a conjecture by Adolph and Spencer. Nonetheless, they could not prove. They conjectured that threshold for the appearance of the giant component should be what branching process intuition would tell us. In a way, branching process forgets about structure, right? Because it's a tree, infinite tree. On the other, our hypercube potentially might have C4s, a lot of C4s. So look, locally, they are far away, but because we make it so sparse, what it says is that locally maybe it's a tree-like, therefore this intuition might be correct, right? So proving it another matter. This is just conjecture, yeah? Guessing and proving. So they, through this heuristic, they guessed, and then it was proved by Aitai, Komnosh, and Semeredi. Yeah, all these very famous names in external graph theory. Aitai, Komnosh, and Semeredi proved that indeed it is the case. But then Polobash, Koyakawa, Uchak, yet another 3 names, the main contributors in random graph theory, they improved their result. In summing up what it is, you don't need to read. We can go one by after another 2. So let's say D times P. D times P is what? For each vertex, how many edges will I see on average? Because it was independently, so I have a D potential neighbors. We had success probability P, therefore D times P will be expected degree of a random vertex. So expected degree is now, let's say, is a constant C, and let Li be the ith largest component. Yeah? First, second, and third, blah, blah, blah. Then, what they prove is the following. With probability tending to 1 as D tends to infinity, but you just think of D is very large, and probability, with a high probability, WHP, meaning that like 1 minus peak of 1 over D, if you want, yeah? With the tending to 1, what we can show is the following. If the average degree is smaller than 1, then it's very likely that the largest component is at most D, contains at most D vertices. D was a dimension. Number of vertices is 2 to the D. It's indeed a log of the number of vertices, yeah? So which means the size of the giant is indeed logarithmic in the number of vertices. On the other hand, the supercriticality, like a branching process, right? In the supercriticality, the size of the largest is linear in D, 2 to the D. 2 to the D is the number of vertices, while second largest is small. What is rho C? So this is 2 to the D is number of vertices. So now rho times C is, in other words, if you scale by 2 to the D, it's the asymptotic fraction of the vertices lying in the giant. But then this fraction is indeed same as the survival probability of the Galton-Watson branching process with offspring distribution Poisson C. Heuristic is correct. You can convert the heuristic into mathematical proof, and this is done by all these giants. They are in the random graph theory really giant of the giants. Any questions?
What happens if C is equal to 1?
Yeah, very good question. It's a so-called criticality. In the criticality, the picture is more complicated. If you order or the size of the giant and scale it by n to the third, then it's a constant. But there are so many such components. You can model it by a Brownian expression. Length of you consider a sequence of rescaled size of the giant, rescaled by n to the third. Then it's a constant C1, C2, C3, C4, blah, blah. And this mimics so-called multi-coalescence Brownian motion and the length of the so-called Brownian expression. Very complicated, yeah? Nonetheless, the order is big theta p of n to the third. It's too much information, so you can just, as a take-home message, it's very complicated, and the order is about n to the third. Very good question. You might think that there is a jump from logarithmic size. N is indeed 2 to the d, sorry, n is 2 to the d. To the n, and then n to no, indeed it's smooth. You can also show that it's indeed smooth. Yeah? It's a very indeed, important question and very tricky question. This, you see, this classic, right? Yeah, more than certain years ago. But then around this hypercube, there were so many other questions that we want to ask. If it's related to your question indeed, if the average degree is now just a little bit above the criticality, 1 plus epsilon. But nonetheless, epsilon is a constant which is very small. Often the case that if I want to answer your question, I have to let epsilon tends to 0 and have the right scaling, so-called the critical window. It's too complicated for this particular talk, so I skip. But let's say epsilon is a very small, tiny constant. Yeah? So 1 plus just above the threshold, right? 1 plus epsilon. Therefore, I call it early giant. What can you say about the early giant? It's just born, just above the threshold. And then there were so many questions asked, but apart from this range, it's a very complicated range indeed. This early giant is usually, it's more complicated than the others. It's not yet stable. And then already Isaac Gomnoshin severity asked, what is the likely typical length of the longest cycle in L1? And indeed, Hong Liu had a positive result in this direction using Brooks many years ago. Then another open question in this direction was also by these people. So what is the likely diameter? Because we make it so sparse, locally we see only 1 plus epsilon children. 1 plus, it's a very sparse. So potentially diameter, before population it was D, because every path is, now it's so sparse, it might be that we have to go via, and it could be even linear in 2 to the D potentially, because so sparse is like a tree. So what is it? The other regimes, the answers, the no answer. The most difficult and unsolved range is this so-called early supercritical regime, we sometimes call weakly supercritical regime, or barely supercritical regime. And then there was another question which is coming from even more probability theory. You look at the so-called simple random walk. You go to one of your neighbor with equal probability. I'm here and I select one of my neighbors, uniformly random, I go there. It's usually 1 over D. But then using some general theory from probability theory, if you do such a so-called simple random walk on bipartite graph, you will always be returning to the same place. It's common. To avoid such a situation, it's not ergodic. You stay where you are. So-called lazy. With half a problem, I will stay, and then I decide where I go. Then the Markov chain becomes so-called ergodic, and then therefore blah blah. So you can talk about the mixing time. So mixing time is a typical question, and also for different P, the things are answered. The open questions are in this range. And luckily, together with my colleagues some years ago, we could say something. In this early giant has a so-called large circumference. The length of the longest cycle is almost optimal. So 2 to the d is the total number of vertices. If a cycle covers 2 to the d vertices, we call Hamiltonians, Hamilton cycle, but we cannot guarantee. But 2 to the d up to some poly in d, we can guarantee a long cycle. At least it's a low bound. Yeah? On the other hand, diameter theoretically could be 2 to the d because we made it so sparse, but nonetheless it's polynomial only. Before calculation it was d. I can just go directly. Yeah? So we have to make little detour, but not too much. 2 to the d, and we go it's perfect. And mixing time, it's also poly in d. But then there was a question in the audience, can you improve it? Can you improve it? So we were kind of it's not very junior people, so we were a little lazy and oh yeah, you can do but yeah, but then we had a very clever PhD student, Diskin, to see, it's just the same name, but then one addition. This one addition was very clever and diligent PhD student of Michael Kravlich from Tel Aviv. He will become a postdoc from 1st of September in 88, Zurich. Yeah, with him you see a lot of improvements. This is a minor improvement. The diameter is almost optimal in d. D times poly d. It is very huge improvement. Mixing time is also almost optimal because in this regime, the giant component has a so-called two-core and the very long so-called bare path. Bare path is like a random walk on a one-dimensional integer one-dimensional integer lattice is a very strange wording, but we call it a one-dimensional integer lattice. And if you start from a middle point to go to the other end, you need so something. So d square is the optimal. So lower bound is d square, and what you prove is the upper bound is d square times poly d, polylog. Yeah, it's almost optimal. Thanks to him. Yeah, from 11 to 2 to the d, it sounds like polynomial improvement, but what I'm saying is that lower bound itself is d to the d, so it's a huge improvement thanks to the joining PhD student. Diameter is also, because we saw that before calculation it was d, is almost optimal. Yeah? About the method, we indeed this is true not only for Hypercube but more general model, so-called Cartesian product of bounded regular graphs that I will come back. So whatever there are generalizations, you will see. The more important thing is it's all not straightforward, but in a way consequences of the so-called expansion properties of the giant. There is a folklore, if the graph has a nice expansion, then it guarantees a large matching, it guarantees long cycles, it could expand, small diameter because it expands well, so you can reach from one point to the other so quick. Mixing time, small mixing time, some of the times they are equivalent. It's not only one direction but equivalent. But of course in our random graph theory, we are very much interested in this quantifications, not quality but quantity. So anyway, so this is the thing. So it's a kind of not direct but kind of following the general philosophy consequences of expansion properties of the giant. So let me talk about these expansion properties, what I mean by that.
So for the second last comment, do you mean that is true for both papers?
Yes. We did in the first paper we didn't care about the Cartesian product graph because of these open problems, because we solved the 3 open problems, the long-standing open problem. Yeah. And then the Sahar wrote one day, I was in Dortmund, I think. Once upon a time, wrote an email. Oh, indeed, your method works for a arbitrary. And I said, oh wow, what is this?
It is the
interesting. What is this model? I've never thought about it. And then he mentioned, yeah, this is a very nice class. So let me talk about what is that, right? Because I didn't know 3 years ago, let's say. I think it was about 2021. So what is it? Given a sequence of graphs, let's say G1 through GT, because I want to keep the D as indeed a regularity. So T will be my dimension. It's not usual notation. Usually people call n-dimensional over d-dimensional, but n for me is the number of vertices. D is always regularity, so I keep T. T. I have a T graphs, whatever they are, finite graphs. And then the so-called Cartesian, there are so many product graphs, so Cartesian product graph. Why Cartesian? Because their vertex set is a Cartesian product of the other vertex. Yeah? So what am I doing? This one. This one. The vertex set itself is a Cartesian product of the vertex set. In other words, it has a coordinate system. Vertex consists of V1 through Vt. Each Vj comes from the jth base graph. Yeah? Huh? Coordinate system. And then what is an edge set? Edge set, there is an index in the single index j such that uj and vj's are edge in the original base graph, jth original graph, and the other coordinates are all equal. So you can imagine. So indeed, it's a generalization of the hypercube, the dimensional hypercube. How do you get it? It's a d copies of K2 edges. D copies of edges. 2 copies of H will be C4. C4 together with the C4 merged by perfect matching will be 3 cube. 3 cube by perfect matching will be 4 cube and so on. Yeah? So the hypercube is just Cartesian product of K2. Torus, the dimensional torus is a D copies of cycles of length L. Just multiply. By definition, and Hamming graph is Cartesian product of complete graph. It's a nice generalization of, we think, or Diskin convinced us, Diskin convinced us. Indeed, it is a very rich class, it's a graph. We cannot prove everything in generality because of something. Yeah? So our technique allows us to the following setting. I didn't say, so I have to go back. So we could prove analogous thing because we need D regularity, bounded regular. So Cartesian product of regular graph so that the product graph itself becomes D regular, so D comes down. To the D will be replaced by the number of vertices coming from the Cartesian product, and they are connected. Otherwise, things you can have separate components, and it's difficult to talk about the giant components. So it's a bounded, regular, connected graph. Then it works. Yeah.
Because the bounded means that each graph has bounded number of vertices.
Yeah. Let's say 100, 1,000, doesn't matter. But it's a number. It's independent of D and the dimension. Yeah. So now the consequences. What do I say? Expansion properties are very important. What are they? They are indeed very popular. There are even many surveys by Allen and Huri, Lineal, Vidocson, Criticality. All these names suggest that indeed it's applicable in many places like computer science, geometry, I think, Chico constant in manifold and so on. So Vidocson is also computer science and complexity theory and so on. So it's very applicable. If you haven't heard about it, because I see that there are kind of junior mathematicians here, if you haven't heard about it, it's really useful. What is it? Given a graph H, I do not want to call G, so given H, you look at the so-called external neighborhood. Given a set S, you look at the neighbor in the complement of S. So on the outside, neighbor, outside, we call external neighborhood. The definition is there, but it doesn't care. The picture says more. So given an S, set S, subset of vertices S, you look at its external neighbor. And you look at the ratio between the size of the external neighbor, the green vertices, comparison to the size of S. You look at its ratio, and you look at the minimum of all possible vertex subset. Yeah, due to symmetry reasons, you don't need to go that far. Just a half is enough, but don't need to think about it too much. Yeah? You look at this one. and you look at, you call it as a vertex expansion ratio because we look at the neighbor of the vertex set. Then there is also edge expansion property. So edge expansion ratio, what is that? Now you look at the number of edges with one edge in one end in S, the other end in the complement. There will be these blue edges between two. Yeah, S and its complement. You look at the so-called edge boundary, we call edge boundary. These blue edges we call edge boundary. Okay, the crossing edges. How many of them are there? Comparison to the size of the vertex at S. You look at the minimum possible, and we call it edge expansion ratio. One of these two concepts are sometimes called Chiga constant, although they are not the same. If you come from probability theory, they might call it conductance. They are not the same, but you can transfer from one to the other. Or the spectral gap, yeah? Spectral gap, if you don't know, forget about it. If you know, it has to do also equivalence to the spectral gap. Sometimes one direction implication, sometimes both directions. Yeah? So these are the so-called vertex expansion and edge expansion properties. If you look at the D-regular graph, you can think of, you can derive from one from the other, huh? If it's a D-regular. So just a comment. So these are the expansion, vertex expansion, blah, blah. What can we say about the hypercube? Is there any nice expansion property to be able to show that the global expansion properties can be very bad? But if you restrict ourselves to sets of given size, let's say K, then you can say better, something more final result. And this is why we have refined version of the so-called Isoperimetric parameter, namely, you restrict ourselves to the size of the set, vertex set is now K. Given K, we want to define the so-called expansion Isoperimetric parameter to be the same as before. Yeah? Size of the edge boundary divided by size of S. Size of S is K now, right? But we restrict ourselves only those sets of size K. Yeah? Then, of course, our original HS parameter inequality can be recovered, of course, by that. Yeah? Anyway, so this, you can see that this is refined version. Because the global is just minimum of that. Yeah? It's a worst case scenario. So in terms of this refined version, there's a classic result by Harper. It's so famous, okay? Harper's inequality. If you do any Isoperimetric inequality, you always hear about Harper's inequality. Harper's inequality says that in case of the hypercube, yeah, this K is the size of the subset, is at least D minus log 2K. D was the regularity. If K is small, small sets achieve the best, right? If K is small, it's almost optimal. Of course, then K is large because it can go to, sorry, this is 2 to the D. Yeah? Once upon a time, I hope the N was the size of the 2 to the D was equal to N. I think I read somewhere anyway. 2 to the D, you can go to the D. If it's the case, this is 0. No information, right? So anyway, so refined version gives us stronger final result, and this is so-called Harper's inequality. And we were wondering, what can we say about edge Isoperimetric parameters for the Cartesian product graph that I was talking about. Because I told you that the result that I was mentioning is a consequence of this expansion property, so I have to say about that. This is answering also Sangye's question. So we consider Cartesian product graph of bounded by L, bounded connected regular graphs, they are the base graphs, and the Cartesian product, you make it, and then you obtain the regularity of the G. So because of the definition of the Cartesian product, we have the sum of all degrees of the base graph. Yeah? And the number of edges is just coming from the blah blah. Yeah? So product of the vertex, size of the vertex sets of the base graphs. Yeah? So I just write it there. Mm-hmm. Then what I said was the following, without calculation. Yeah? Such a Cartesian product graph has a very nice such a Isoperimetric inequalities in two ways. Why do we need just such a 2? So let's take L equals 2. L equals 2 was the hypercube, right? Because hypercube, the base graph has a size 2, so L equals 2. If you take 2, exactly the same thing that you obtain. D minus log 2D. the same thing, right? Why do we have two things? If you look at K large, I told you, it gives nearly no information. For large K, this gives some information, better than the other, yeah? That's why we have these two depending on the range of K. Using this, we did it, and then this clever PhD student, Diskin and Samoti used to visit here, some of you might have met him. They obtained not this explicit formula, but some other, using some very nice function. They also studied Isoperimetric inequality for arbitrary product graphs, not bounded, connected, yada yada, without, yeah? But I told you, if you do not specify the graph, the formula is very general, but nonetheless is in a way implicit, yeah? So if you fix your input graph, theoretically should give an optimal, but indeed sometimes not very optimal because it's such a general formula.
So I don't understand this because like
Which one? This one?
yeah, so by arbitrary product graphs, so you can include the arbitrary graphs also by just taking the just one. You really,
It's really arbitrary. As I told you,
really?
it's some optimization problem.
okay.
You look at some function so that it reaches something, you define such a function, I will not say because it doesn't give any information, and as a solution of that function, you can have lower bound. That's why I told you optimality, because it is a inequality,
Yeah.
but if you specify particular hypercube, let's say, not necessarily optimal.
So when you say arbitrary, which condition do you remove? Do you remove like bounded
Regularity, boundiness, yeah,
everything?
maybe
Only the only the Cartesian product.
Cartesian product of arbitrary graphs. So in our case, this is a holding for connected, and for this we don't need to have a connecting indeed. Even this one, we don't need to connect. Anyway, yeah, this is a one direction. But then I told you, the long cycle, small diameter is in a way guaranteed by a good expansion property of the giant, because I have to talk about after population. So after population, yeah, so the same thing. Yeah, now G is not any longer just a hypercube, but Cartesian product of the thing that we have seen. What I just abbreviated as D regular n vertex product graph, but this is exactly the thing that I was talking about before, in a slide before. Now we take a random subgraph of that with H probability P. Yeah? Then now we look at this early giant phase, namely it's just above the supercritical regime, so-called barely supercritical regime. Then the giant expands pretty well. You cannot hope for something constant expander, because our graph is so sparse. They are not just constant expander. If you think about expander graph, the vertex expansion ratio and the edge expansion ratios are always constant. No, they are at least some constant. We cannot hope for it because our graph is so sparse. Nonetheless, it's 1 over d log d. It's not too bad because we made it with a probability p, which is almost 1 over d. We are making everything sparse, 1 over d sparsification. But nonetheless, we can guarantee such a strength. Yeah, it's strange for you, right? Because 1 over d log d, it tends to 0. Expands very badly. Indeed not, it's not too bad, yeah? And if from that, if the graph is d-regular, vertex expansion ratio of the largest will be 1 over d squared log d, because every edge, because of d-regularity. But we can indeed improve in a way that giant contains a subgraph of linear order, which has a better vertex expansion, namely 1 over d log d instead of 1 over d squared. As I told you in random graph theory, we do everything quantification, but nonetheless, it's a good expansion. Good expansion guarantees long cycle, small diameter. Yeah? So quantification, so you have to work harder to achieve that, but nonetheless, this is the take-home message. Now, there is in a way the so-called universality phenomenon in probability theory. Our inspiration comes from this branching process, if we look at it. Yeah, it doesn't matter what is the underlying graph. If we look at very sparse regime, maybe they look all the same, locally tree-like. But nonetheless, there are things locally tree-like, but maybe like a thin tube. But then if you percolate, it results in two giant components, meaning the two separate component of linear size. It's not, in other words, the giant components are not unique. So we want to guarantee such a Edo-Shirani phenomenon. I didn't mention, but anyway, so we want to guarantee such a thing. In order to guarantee that, we can do the following. This is the previous, but we can do the following. Yeah? So given any irregular n-vertex arbitrary graph, it's not necessarily product graph, yeah, because we've worked on product graph. Why do we need this product? In the proof, we need product structure because we use so-called projection, whatever, this coordinate system. But we were wondering, is it just something special about coordinate system or product, or is it general? Indeed, we want to say, yeah, so now, the irregular n-vertex arbitrary graph, no product structure. Then we take a random subgraph of that with H probability P. You can think of it as well, right? D regular graph, what can we say about it? But our point is D is large, yeah? But then, what we can guarantee, has been studied is when D is constant was first. If D is a constant, because we start from one vertex, so the root is special. If you look at somewhere, because I came from somewhere, I have to eliminate this effect. So I have only D minus 1 potential children. So threshold is 1 over D minus 1. If D is large, 1 over D minus 1, 1 over D, they are ignored. They are the same order. But if this is a constant, 1 over 2 is different from 1 over 3, right? If D is 3. So therefore, it's very important that it's 1 over D minus 1, blah, blah, blah. And for high Gauss expander, I told you that the expansion parameter is constant. Then the uniqueness is guaranteed, and the order of the giant has been studied by various combinations of big shots in random graph theory. Yes, it's a very fundamental question about the uniqueness of the giant and the order of the giant. It's very much studied in literature when D was constant, and then because of the inspiration coming from the high dimensional hypercube, we look at when D is not a constant. Indeed, we can also guarantee that just a single constant H expansion guarantees a unique giant component of the correct order. This is the survival probability of the Gauss. Yeah? A single H expansion, but constant expansion guarantees the uniqueness of the giant component of the correct order. Having said that, we will even want to talk about even further. Yeah. Because if you look at it, this is about just a unique giant component. But to be able to talk about other internal structure of the giant, I need, if I want to talk about circumference, if I want to talk about diameter, what was essential? Let me check whether you heard my talk. What guarantees such a thing? Expansion, right? Expansion. Therefore, we ask one step further. Is this global edge expansion guarantees that? Indeed not. Otherwise, I will not ask. We need a little bit of control over the locality. Yeah, it's not only the global, because the global is everything, right? Small sets, large sets. Everything minimum. That's worst case. Therefore, what we have to control is indeed small set expansion. Yeah, you don't need to read it. Small sets, if they have a nice so-called local expansion, I know that in structural graph theory you are also talking about localities. It's a very, very important concept, global and local, how they interplay with each other. Qualitatively, if we can guarantee the base graph has a nice global edge expansion and also nice local expansion of small sets, then we can guarantee that giant has a very nice, not very nice, but decent edge expansion. Because I told you in random graph theory, we do care about quantity, not quality. If you are curious about quantity, here it is, but I think you don't want to read it, yeah? We can quantify it, but don't read it, yeah? So now let's talk about large matchings. Large matchings are guaranteed also by this expansion property, but you can do better than what expansion properties will say us. let's go back to the original problem. Like some years ago, Balabolova showed that 1/2 is a threshold for the perfect matching in the calculated hypercube. Just in case, some of you might remember in the Erdős-Renyi random graph GNP threshold. Maybe home. You came from also from. What is the threshold for the Erdős-Renyi GNP? The Hamiltonicity threshold. Once upon a time in our life, log n. Very good. Log n over n. P is log n over if you take the base graph as a kn, complete graph kn, if you do the random subgraph as we do, then we obtain the so-called Erdős-Renyi random graph G n comma P, the most famous random graph model. Yes. Log n over n. It's pretty sparse. But on the other hand, because our universe is so large, 2 to the d, in order for calculated hypercube to contain a perfect matching, you need to go that far, 1/2. Constant probability. So Sharpe's threshold. What is a Sharpe's threshold? It's just definition. For any, if p is smaller than 1 minus epsilon times 1/2, then no, with probability tending to 0, blah. Yeah. So 0 on statement, depending on large or small. Just to write for the sake of the younger people, but otherwise the take-home message is that 1/2 is just Sharpe threshold. It's not just a coarse threshold, but Sharpe threshold. This was a question. Now, if we are not aiming for the perfect matching meaning that the set of the edges, set of vertex disjoint edges, right? This is a matching. Perfect if every vertex in a graph is incident to a matching, then we call perfect. Now, in order to guarantee this perfect matching, we have to go that far. Now, we are not aiming for perfect matching, but maybe just almost perfect matching, like 1 minus little o of something times 2 to the d, let's say. If we are not aiming for everything, but we allow some error. How small can we make? How small we should go so that it's a nearly perfect matching? What do you say? We don't know. But then we realize it's pretty easy indeed. Not easy, but hindsight it's easy. That if your average degree d times p is just large enough, any concept but large enough, 100, we didn't optimize, yeah? 20, it's not 1, huh? 20, 100. Okay, then indeed you can guarantee nearly spanning matchings. To be perfect, you have to go that far, right? P is equal to 1 over 2 versus P is like 100 over D. It's very sparse. Nonetheless, you can guarantee almost spanning. It's indeed hindsight, it's easy. You use so-called the peeling process. You peel out the vertices of small degrees recursively so that you guarantee that there is a subgraph so that maximum degree is just what it should be, right? Average degree is like d times p is about c, and this c, but you just make sure that it's larger things you peel out, delete, but then you can also guarantee the number of edges is not too small, but then using so-called Vizing, you can guarantee a much. If you don't know, you just type Google, what is Vizing? The edge coloring. Anyway, so now we guarantee how to make almost spanning matching. Once you do that, another level is we are usually interested in the extremal quantities, like what is the maximum cardinality of the largest matching. If you want to make it sparser, because to have an almost perfect matching, we have to guarantee that average degree is a large constant. Now, you look at the arbitrary constant, like even 1 or 1/2 even, yeah, C, average degree. Can you say something about the cardinality of the largest matching, the largest possible matching, so-called matching number? Matching number is also one of the quantities studied a lot by Kapsipsa and so on in the random graph. What we could proudly say is that the matching number divided by 2 to the d minus 1. T to the 2 to the d minus 1 is the size of the perfect matching, right? number of edges in a perfect matching is 2 to the d over 2 because the 2 edges. This is the size of the perfect matching. Comparison to that, it converges to 1 minus some strange number. I already talked to Kolang, right? You asked me where this phi function comes. It's so-called vector free energy. For you, it's just keyword. It's coming from some other so-called belief propagation, but you don't need to know anything. Yeah? It's just one variation problem, namely C is given, and then it's a function in alpha to blah blah blah. Yeah, you don't need to. There is such a function, and then you can say that the matching number converges to do that. Interestingly, this has to do with the matching number of the address Rennie of the same constant degree. And also answering your question, it's also the rank of the related matrix. What could be the adjacency matrix? We need bi-adjacency matrix because our graph is bipartite. Rank of the bi-adjacency matrix divided by the number of edges also converges to the same. Matching number has to do with rank. Yeah, now long cycles, because I have only 5 minutes, it should be very quick. Once upon a time, many people conjectured and reconjectured and reconjectured, you see, that indeed 1/2 is also a threshold for the Hamiltonicity. To guarantee Hamiltonicity in GMP, we need also log n over n, but so because of some intuition, people conjectured, and we can really claim this long-standing conjecture, and this has been proved very recently by people in Birmingham. Of course, some of the people left Birmingham, but nonetheless, it's a breakthrough result. I think it's published in MS Memoirs, Memoirs of MS. So that 1/2 is indeed a sharp threshold for the Hamiltonicity. Perfect matching, Hamiltonicity has the same threshold. Indeed, it's the connectiveness threshold, also the same. Having said that, like in matching, if we do not want to guarantee the spanning cycle, but nearly spanning, that every vertex is contained in a cycle, but almost every, then what can we say? Do we have to go that far? Like 1 minus epsilon over 2, or can we go even sparser? Yes, we can sparser. And then there was a conjecture, even folklore. Yes, and authors and people believe that if average degree grows, like log d, whatever function that is, the percolated hypercube should contain nearly spanning cycle. Indeed, very recently we could confirm the conjecture in a stronger form. We can make a quantified version of the conjecture. Namely, if the average degree is large enough, large constant, say 100, then you can guarantee nearly spanning cycle. Having this said now, what can we say? If we make it even sparser, if d times p is just constant. Oops, I have a proof sketch, but I think I don't have time because I think it's more educational if I talk about this, I think, yeah? I think I have a sketch proof, but maybe we can do this Q&A session. I guess there will be Q&A. There's a very, very easy 3-step proof. Apart from the pre-processing, so S0 is pre-processing, so in 3-step, so we could prove this conjecture, indeed the long-standing conjecture, with a very nice. So, of course, talk cannot finish without open questions. I pose the canonical candidate, namely, we look back, we return to the hypercube, where d times p is a constant, larger than 1. With my colleagues, we could study when d times p is 1 plus epsilon, just, barely supercritical. Now we are talking about whole range of the supercriticality, not only just right after the birth of the giant. What can we say about the correct order of the circumference? We believe that the order should be 2 to the d, but we had this d square over d square times log d in the denominator as a lower. Also, diameter is the correct order of the diameter, just linear in d. We had a d to the 3. Mixing time I don't talk about. Yeah. So, yeah. Thank you very much for your attention. chemical room.
If this theorem about matching number
Yeah.
divided by 2 to the minus 1, was it ever like previously conjectured by physicists? It's like they might.
Yeah, very good. There was a conjecture not by physicists but French probabilists. Not the matching number, but the rank. There was a conjecture because indeed during the last 2 years or 3 years there was a lot of development in that direction. To make a comparable to that, let's talk about the pi case, yeah? G, n, p, but in order to have a comparable thing, C over D, yeah? C over n is the comparable model, right? Pi graph with the average degree C. When you look at the bi-adjacency matrix, the bi-adjacency matrix you can model as a 0, 1. So binary matrix whose entry becomes 1 with the probability P model we are talking about. Then the rank of that model divided by n converges to that thing. The free energy, vector free energy, vector free entropy, sorry. Yeah? But then, there was yet another result by your French colleagues, Bodenave, Lalage, and Chalet. Indeed, they proved that this is indeed the same as this matching number of them. Indeed, this is the Bodenave, Lalage, and Chalet. Indeed, in their proof, it's not only about, indeed, such a model. You take any graph sequence, which allows a so-called Benjamin-Ishram local reconvergence, then blah, blah, blah. Yeah? It's a very general theorem, and the only thing we did to achieve that is indeed, we guarantee that our graph has a local weak limit. Its Benjamin-Ishram local weak limit is a Galton-Watson branching process with offspring distribution Poisson C. Having that said, this is a corollary of a very general setting, namely if your given graph is almost irregular, it's not irregular, almost irregular, we allow some errors, it's almost irregular, then indeed its local weak limit is Poisson C, Galton-Watson tree, and therefore it is a corollary by Bodenave, Lalage, Chalet, you can obtain such a universal property. Interesting thing is the connection to the rank is more important, and this is obtained by their formula is not necessarily the same, but hindsight they are the same, and this is indeed the so-called by once upon a time if you work on the algorithms or CSP problem you might hear so-called belief propagation algorithm or the warning propagation message passing, whatever. So belief propagation message passing algorithm gives such a thing. Yeah? So this is interesting. Yeah. Okay.
Any other?
Yeah.
Yes.
Actually, in the GMP branch, GMP phase transition model, actually we need to introduce a fine parametrization. That is, NP equals 1 plus the n to the minus.
If you want to open up the window, I say it by passing when he asked it. Yeah, it's a so-called critical window. In the critical window, I already said in GMP.
I mean they
If the
still
P, wait. P is n times P is 1 pi epsilon, where epsilon tends to 0. It's not enough indeed. It has 3 regimes. If n to the 1 to the 1/3 tends to negative infinity, so-called weakly subcritical, when n times epsilon tends to constant. Constant is constant. Any constant, or n to the 1/3 tends to positive infinity. Then the size of the giant is epsilon 2 over epsilon minus 2.
So what is? So
No,
this
okay.
is for GMP, right? So
Yes.
do we have similar results for the cubes or for this quantitative?
That's
No, because determining the so-called the width of the critical window is trickier than you might think. Even better, is it recorded and you will put in the YouTube, right? Thanks to the Bela-Bolobash Uchak, we know the correct width of the critical window, but it was not clear at the beginning of the study of the random graphs. Yeah, it's indeed a very difficult thing. This is theta p of n to the third. Of course, everything is with high probability. In this case, is about 2 epsilon times n. You see the smooth phase transition, that's what I'm saying. If epsilon is about n to the minus 1/3, alpha times n to the minus 1/3, if you plug in, you calculate, it smoothly move from that to that. Yeah, smoothly, depending on epsilon. If you plug in, what's going on? It's smooth phase transition. Yeah, thanks for mentioning that. It's a tough stuff. Indeed, my specialty is indeed this one. For other graph models, but populated hypercube is more complicated than you might think.
Any other questions? If not, let's thank the